So in this example here, we're asked to find the Fourier transform of the signal x of t that looks something like this. Okay. Now suppose this x of t looks a little bit odd, right? But if you take the derivative of x of t, then it gives us something more familiar. Okay. So suppose you let g of t be equal to the derivative of x of t. Okay. So when you take the derivative over this slope here, right, you should get a constant 1. And for these two parts here, you should get a constant 0. Okay. So this will give you a part that looks like a rectangle from -1 up to 1. Okay? But that's not all. Right? If you look at this figure here, we also have an abrupt change from 0 to -1 at position -1, and also an abrupt change from 1 to 0 at this point 1. Okay? So when you have this abrupt rise or fall, this corresponds to a delta function with the derivative. Okay? So this will give you also two negative delta functions. Okay? At position -1 and 1 to account for this abrupt fall on the edges. Okay? Now these functions are familiar to us. Okay? We know what their Fourier transforms are. So we can derive the Fourier transform. Right, let's call it g of j omega. For the rectangle, right, we get a sinc function. That is 2 sine omega over omega. Okay? And for each one of these delta functions, we have a pure complex exponential. All right, so one at frequency omega and the other at frequency minus omega. Okay? And if you combine these two, this, by Euler's relation, this gives you -2 cosine omega. Okay. So finding the Fourier transform of this signal x of t may be not as straightforward, right? Because x of t takes on a shape that is less familiar to us, so the derivation may be a little bit tedious. But if we look at the derivative of x of t, right, which gives you a function g of t, then we can see that g of t is composed of two parts that are, quite familiar to us, and we know directly from previous derivations what their Fourier transforms are. Okay? So then, given g of t, you can go back and find the transform for x of t by this integration property. Right. So we know that x of t is the integral of g, and it should have a Fourier transform. Okay, that is g of j omega over j omega plus pi g of 0 delta of omega. okay? Then I just take this g of j omega, plug this inside, and this will give me one over j omega 2 sine omega over omega minus 2 cosine omega. Okay? Now I also have this term here. Now when omega is not equal to 0, delta is 0, right? So there's no problem there. But for omega equal to 0, right? For omega equal to 0, then you have this g of 0, right? You have something non-zero scaled by this g of 0, okay? Now what is g of 0, right? If you plug in omega equal to 0 here, right, this sinc function will give you a constant 2, and cosine omega is, cosine 0 is 1, so this gives you minus 2, right? So 2 minus 2 is 0, okay? So g of 0 is 0, right? So the second term has no contribution, all right? Okay, so this then gives you the spectrum that you're looking for, right? The spectrum of this signal here. Okay. Now, interestingly, you can see that since the time domain signal is real and odd, you can see here that this signal is real and odd. Okay. Therefore, its spectrum is indeed pure imaginary, okay, and odd. So we have a few more properties to go, okay. So the next property is this time or frequency scaling, okay. So this says that, you know, if you scale the time domain by a, then the Fourier transform will be, you know, 1 over the absolute value of a times the spectrum scaled by 1 over a. Okay, so if you scale the time domain by a, you will scale the spectrum by 1 over a with this additional constant. Okay. So you can show this by directly performing the Fourier transform on x of at. Right, so suppose you compute the Fourier transform of x of at. Right, by the Fourier transform formula, this gives you x of at times e to the minus j omega t dt. Okay? Now let's do a change of variable where you let tau be equal to at. Okay? And suppose first that a is greater than 0. Okay. So if a is greater than 0, right, then we have integral x of tau times e to the minus j omega tau over a d tau over a. Okay? So t becomes tau over a, and dt becomes d tau over a. Right? Now, when a is less than 0, okay? So when a is less than 0, then, this is the same, right? A of t becomes tau, t becomes tau over a, dt becomes d tau over a. But now, now when a is negative, right, when you perform this transformation, the integral becomes from infinity to minus infinity. So if you want to switch the order, you need to add a negative sign in the front. Okay? Oh, I'm sorry. This is just the a on the bottom. Okay. So this integral here, right, this integral here, not including the a, right, this integral here, is just the Fourier transform of x at frequency omega divided by a. Right? Similarly here. Okay. So this becomes 1 over the absolute value of a, the spectrum of x at omega over a. Okay? So this 1 over absolute value of a is obtained by extracting this 1 over a outside, right? So if a is positive, then we have 1 over a here. If a is negative, then we have 1 over minus a, right? Minus a gives you a positive value, so we can, represent them concisely as just a single absolute value of a. Okay. So what's interesting about this property is that it tells us that if you scale the time domain by a, then you're scaling the frequency domain by 1 over a. Right? So assuming that a is greater than 1, for example, with a equal to 2, then scaling the time by 2 means that you're fast-forwarding the signal by 2 times. So in the time domain, you're basically compressing the signal in the time domain. Okay? So if a is greater than 1, then you're compressing the signal in the time domain, but you're expanding the signal in the frequency domain. Okay? So similarly, if you have a less than 1, then you're expanding the signal in the time domain, but then you're compressing the frequency domain. Okay. So this is a very important property regarding this time and frequency domain relationship. Okay. So compression in time corresponds to expansion in frequency. Okay, and vice versa. Okay. So this is not surprising, right? Because when you compress the signal in time, right, this means that your signal, suppose it varies this fast, now when you compress it, the signal is now varying faster, okay? So when your signal varies faster, it means that it has higher frequency components, okay? So it basically means that your spectrum should include more high frequency components, basically expanding the spectrum, okay? Right. Now, consequently, right, if you choose a equal to -1, right, then this corresponds to a time reversal, okay? So consequently, with a equal to -1, you show that a time reversal has a Fourier transform that is equal to the frequency reversal of the spectrum. Okay? Right. So this is a very important point. Right, so I would emphasize this. Okay. Okay. Now another useful property is this duality. Okay. So the duality we already mentioned a little bit before. Okay. So this duality comes from the symmetry of this Fourier transform pair. Right? If you observe this Fourier transform and the inverse Fourier transform formula, you can see that they look, almost exactly the same, except for this negative sign in the exponent, right? And with this additional scale. Right? Other than that, it's exactly the same. Okay? So you would sort of expect a symmetry going from time domain to frequency domain, or from frequency domain coming back to time domain. Okay? So in fact, you can show that if you have, right, we've actually shown this, right? If you have a rectangular shaped signal in the time domain, then in the frequency domain, you have this sinc-like function. And similarly, if you have a rectangular shape signal in the frequency domain, then its time domain will also take on this sinc-like function. Okay? And this is due to this duality property. All right. So this often, this often simplifies your computation of either the Fourier transform or the inverse Fourier transform. Because often it's easier to go from one form to the other form, and not as easy to go from that form back. Okay? So for example, here, it's probably easier to go from the square signal to the sinc than the other way around. Okay? So if you know how to do this, then you can actually obtain the Fourier transform of a sinc by this duality property. Okay. Now let's look at another example. Okay. So this is just an illustration of what we just showed. Okay. So this gives you another example. All right, so suppose that you're asked to find the Fourier transform of this signal 2 over 1 plus t squared. Okay? Now, doing this directly may not be, as straightforward. But we know from example 4.2 that a double-sided exponential has a Fourier transform that takes on this form, right? 2 over 1 plus omega squared. So by duality, you can actually show that the spectrum of this signal will also take on this doubly decaying exponential form. Okay? And you can do that by a simple change of variable. All right, so from this relationship here, we know that e to the minus t can be written as 1 over 2 pi 2 over 1 plus omega squared e to the power j omega t d omega. Okay? So from this property here, we obtain this identity. Right? We know the integral of this 2 over 1 plus omega squared times e to the j omega t gives you a form that is this double-sided exponential. Okay? So deriving this integral directly is not straightforward, right? It's not as simple. But we know this identity holds because of this, Fourier transform relationship. Okay. Now we can do a change of variable where we set t prime equal to omega and omega prime equal to t. Okay? So if we do that, then we have on the left-hand side e to the minus omega prime. Okay? And on the right-hand side, we have 1 over 2 pi integral 2 over 1 plus t prime square e to the j omega prime t prime d t prime. Okay? Now let's further change, omega prime sorry. I could have done this a little bit, faster. So maybe I just let this okay. Maybe let me just let t prime be equal to minus omega. Okay? So that can help me, reduce one step. Okay. So in that case, I will have a negative sign here. Okay? So if I let t prime be equal to minus omega, okay, I should have a negative sign here. Okay, because originally omega is changed to minus t prime. Okay? So therefore, if you move this 2 pi to the other side, then what you have here is the Fourier transform of g of t. Okay? So hence, g of t, which is this 2 over 1 plus t squared, has a Fourier transform that is 2 pi e to the minus omega. Yeah. So when you change omega to minus t prime, you should have a minus dt prime, right? But the limit also goes from infinity to minus infinity. So when you switch this around, you get a negative sign that cancels out. 对，谢谢你问这个问题，因为前面有很多推导用到类似的，私底下都有同学来问这个问题，所以应该蛮多人有这个疑问。So by duality, right, you can show that if you have one form going to the other form, then it should also hold that for a signal of this form, you can get back something of the previous form. Okay? Now, not only this, but actually, because of duality, you can show that many of the properties that we showed previously holds both ways as well. Okay? So previously, we showed that for a derivative, it has a Fourier transform that is j omega x of j omega. Okay? And we showed that directly by plugging in the inverse Fourier transform of the spectrum into this x of t. Okay? Now, by duality, you can also show, following the same way, that if you have a derivative in the spectrum, then the time domain will be equal to jt x of t with an additional minus sign here because of the difference in the exponent. Okay? Because of the difference in the exponent when going from one direction to the other. Okay? And similarly, right, for time shifting, we know that a shift in time corresponds to a phase shift in the frequency domain. Okay? And following the same approach that we used to prove this property, you can also prove that going the other way around, a frequency shift corresponds to a phase shift in the time domain, right? And also, there is this negative sign difference in the variable t. Okay. And similarly, for integration, we know that if you have integration in the time domain, then the frequency domain takes on this form here. Okay? Basically, 1 over j omega, the spectrum, plus a bias at 0 frequency. So going from the frequency domain back, you get the same thing, right? The integral in the frequency domain corresponds to this 1 over jt times the signal x of t, again with this negative sign, right? Plus a bias term at 0 time. Okay? All right, so this duality is very useful, right? Because in two ways, right? One is that, if you have the Fourier transform going from one shape of the signal to another shape, then the inverse Fourier transform, it should hold the other way around as well, right? If you have a time domain signal like this, then you should also have a spectrum that takes on this shape.